Today we're doing more limits, more on solving limits. Last time we covered some simple ones like direct substitution, and direct substitution was kind of nice because once you plug it in, you don't get any funny numbers, that's your answer. The limit as x approaches 0 of sine of x, okay? We would just plug it in, sine of x, as you can, sine of 0. As you can see here, I do not write limit because once you plug in the value, we no longer write limit. And the sine of 0 is 0. If you guys forget, sine is your y value, and at 0 degrees, the y value is 0. This is 1, 0 on the unit circle. And if you need help with that, we'll talk about it a little bit later, okay? Direct substitution, one of the easiest ways, just go ahead and try it. What if we end up with a problem? The limit as x approaches, let's say 1 of x squared minus x, x squared minus x over x minus 1. So we try direct substitution. When I plug it in, I end up with 1 minus 1 over 1 minus 1. End up with 0 over 0. We have a fancy word for this. This is called indeterminate. That means try another way. Go figure it out. I don't care. You come up with another way of solving it. And for us, another way of solving it is to factor. So if I factor in x, we end up with x minus 1 over x minus 1. And as we mentioned before, as someone mentioned here, the whole, we do have a whole here, and the whole is here, right? Those divide out. See, that was my 0 value. That was my 0 over 0. How'd you end up with 0 over 0? Because this is 0, this is 0, and this is my 0. But what if they divide out? Now again, in real math, you can't really divide by 0. 0 over 0 doesn't really work. This is all limits. My point is that this value shouldn't have existed. We should have said, screw it, doesn't work. We have a 0 on the bottom. But that stops the conversation. And if you want to say my opinion doesn't matter, right? We could stop here. But we don't want to stop there. We want to continue the conversation. And the conversation says, hey, what if I could divide 0 by 0? They should have divided out. And it should look like limit as x approaches 1 of x, which is what's left. Now we plug it in as just 1. My answer is 1. That's what the limit looks like. The whole is at 1. And that was done using factoring. Now, here are a couple of other problems that we have to worry about. One is square roots. So let's look at square roots now. Okay, so let's use the limit as x approaches, let's use the number 4, use something nice. And we're going to say the square root of x minus 2 over x minus 4. So let's go ahead and plug it in using direct substitution. If I plug in 4, square root of 4 minus 2 over 4 minus 4. Well, this is kind of funny. Hey, wait, this is 0 over 0 again. Another indeterminate, oh no. Okay, that means we have to find another way. So we could run to graphing, and we can graph this out, and we can look at the graph and say, this is what it looks like. But the goal of this is to not always run to graphing. Graphing is kind of our cheating way out. Can I do this algebraically? Now, the gimmick for this, if you guys remember, and you actually did this in pre-calc, is to multiply by the conjugate. So the conjugate of this value here would be, let's go ahead and write limit as x approaches 4. I'm going to rewrite the problem. I'm going to multiply by square root of x plus 2 over square root of x plus 2. So let's go ahead and multiply this out on the top. Remember, we are still writing limit. Let me erase this part here. We are still writing limit. So the limit as x approaches 4. Now, what happens when you multiply conjugates by each other? Okay. And if you do this in pre-calc, it's actually really fast. And you're done on top. Looks kind of stupid, but that's how fast it is. Now let's go ahead and do the math in case you don't remember. So take our time. A square root times a square root is just x. A square root times 2 is a plus 2 square root of x. On the back, negative 2 square root of x. And negative 2 times 2 is negative 4. Okay, I took my time. Is it 1, 2, 3, 4? Now, whenever you do the conjugate, the cool thing is you always get the middle terms to cancel each other out. So don't even bother doing the middle terms. You don't even bother. So that's why we only have the square of the front and square of the back for conjugates. And don't forget to subtract the back term. Okay, on the bottom, here's a hint here. Never multiply these out if you don't have to, unless if you're really desperate. Just leave them as they are because we're going to divide out the x minus 4 anyways. That was our 0 on the denominator. So since we know x minus 4 gave us a 0, we're probably going to divide that out from that top variable. So top part once we're done with it. And you can see now we can divide out the x minus 4. We're left with a limit as x approaches 4 of 1 over square root of x plus 2. We're not done yet. We haven't plugged in our limit. So let's go ahead and plug in our limit. 1 over square root of 4 plus 2 equals to 1 over square root of, 1 over 2 plus 2. And that becomes 1 over 4. Okay, so hopefully you guys can see this. Yep. So on the right here, you'll see that this is the graph of square root of x minus 2 divided by x minus 4. And if you look as we approach 2, oops, I miswrote that, right? Oh, that was 0 approach 4, sorry. Let's get to 4. There's a hole, right? So what does the graph look like? What should it look like? I'm seeing like a 0.25 on one side and a 0.25 on the right side, and left and the right. Okay. So the limit as x approaches 4 of the square root of x minus 2 over x minus 4, this answer is 1 over 4. That's what it looks like. But if I had said, what is the function at 4 of x minus 2 over x minus 4, what would that equal to? And the answer is, it's undefined. There's no answer. So if I tried plugging in 4, like we initially did, we ended up with, it's indeterminate. We end up dividing by 0. There's nothing there. But we don't want to stop the conversation there. Our point is to use limits to say, what should it look like? And when we ask the question, what should it look like? You can apply that to a lot of different, like, big idea themes. Like, what does it look like at the end of the universe? What does it look like if I could split an atom? So it has a lot of applications in physics. Like, because we can't really do it. And if we try doing it, it's almost like, what would it look like if we approach the speed of light? Well, we can't. So should we even start talking about it? And the idea of limits is that we can. What does it look like? Let's go ahead and try. And I can still tell you, what should it be? So the limit is the actual answer for this problem. The value, the function value, is undefined. Is it true that all limits will be undefined? No. When we did direct substitution at the beginning of the problem, looking back here, if I plug in the number and it works, it's a win for us. Oh, where to go? On the top here, oops, how am I writing here? Oops. Just start a new sheet. More limits right here. If I plug in the value, this is what the value looks like on the graph. When direct substitution, when I plug in the value and the answer says 5, the y value is 5. 99% of the time for limits, if you plug in the value, it should work. Only that 1% that kills us. Okay, the limits always tell you what the y value is. We are plugging in an x value and we are getting a y value from it. Okay, now let's look at another problem here. This is another type of fraction problem. A radical. How are you guys doing with this? So whenever we have square roots, the goal is, if it doesn't fit, go ahead and plug in the conjugate, and the conjugate should clean things up. So you can make up these radical problems however you want. They're actually pretty easy. Limit as x approaches, let's say 3, of square root of x plus 1 minus 2 over x minus 3. Now when I plug in the value of 3, we say 3 plus 1 is 4. Square root of 4 is 2. 2 minus 2 is 0. And on the bottom, 3 minus 3 is 0. Hey, indeterminate, find another way. Automatically, we see, okay, I'm stuck. And for all these square root type problems, we always multiply by the conjugate. So let's describe what the conjugate is without doing the whole problem. The conjugate here would be the square root of x plus 1 plus 2 divided by the square root of x plus 1 plus 2. Okay? We do not change the inside of the square root. Think of this as one object. We're keeping the object the same, but the signs between the objects changes from a plus to a minus or a minus to a plus. One of the cool things about this problem here, since it's a fast problem, the top is just going to be x plus 1 minus 4. How'd you do that so fast, Mr. Ko? Remember, when I multiply the front by the front, the square root goes away. What happens to the middle numbers? What happens to 2 plus 2 square root and a minus 2 square root? These numbers would cancel each other out every single time. And the back numbers, negative 2 times a positive 2, would give us a basic 4. On the bottom, it's going to be x minus 3. And we're going to write the square root plus 2. X plus 1. And the limit as x goes to 3. Okay. Remember, we haven't plugged in the limit yet. We are still mixing the equation around so we can find that factor that divides out. And hopefully you have seen already up on top that x plus 1 minus 4 gives us the x minus 3 we need to divide out our 0 over 0, which is kind of cool. It's almost like discovering this puzzle, this x minus 3. It's always been there. It's been in front of our faces this whole time. We then divide it. Okay. And then the next step, we would just write whatever's left after we divide, and then we can plug in the limit. I'll just do that since we're almost there. Limit as x approaches 3 of 1 over square root of x plus 1 plus 2. We can plug in the 3 now. 3 plus 1 is 4. Square root of 4 is 2. This is square root of 4. So 2 plus 2 is 1 over 4. Okay. Just turned out that way. Not every answer is going to be 1 over 4. So what other types of problems might we see? A big deal again is us getting answers that are 0 over 0. Now another one is, let's come up with, let's see, let's take this from, here's my example, and we're going to say it's going to be 1 over, so these are fractions. So I call these Tower of Terror problems because it's going to be a fraction over a fraction. Okay. A fraction over a fraction. And we're at the limit as x approaches 0 here. Sorry, I should have wrote that in front. Squeeze that in front. The limit is always your y value. It's a result of plugging in the x. Okay, so looking at this problem, let's go ahead and plug in our 0. If I plug in a 0 here, and I plug in a 0 here, we end up with 1/2 minus 1/2 over 0, which is 0 over 0. Indeterminate! My fist in the air. Okay, all right. So what do we do? In this case, this type of fraction problem is not the conjugate, totally different problem. That was for radicals. We multiply by our common denominator. Okay, we multiply by our common denominator. In this case, the common denominator is going to be, looking at the fraction, I see a 2 and I see a 2 plus x. So that's going to be our common denominator. So I'm going to rewrite this one more time. Limit as x approaches 0 of 1 over 2 plus x minus 1 over 2 over x. I want to multiply the top and bottom by 2 and a 2 plus x. A 2 and a 2 plus x. And the reason why I'm doing this is I'm trying to get rid of this fraction on top. I'm trying to get rid of all the fractions. Sure, there'll be a lot of leftovers, and this is gross overspending. I don't care. I just want the fractions gone. So I multiply to the front. Doesn't the 2 plus x divide out? And we're left with 2 times 1. The limit as x approaches 0 is 2, because the 2 plus x and the 2 plus x divided out, and we're left with 2 times 1 is 2. On the second fraction, what divides out? The 2 and this 2. So we're left with a 2 plus 1 times a negative 1. So we're left with, let me write it out, negative 2 plus x on the back fraction. On the denominator, I'm going to write 2x 2 plus x. So go ahead and take a look at how I wrote it. It's important that you guys catch it. You can double check. Those divided out. 2 plus x. Divide out. The 2's divide out. We're left with negative sign here. Negative. Okay, let's see what happens. Ooh. The limit as x approaches 0, and we're going to distribute the 2 on the negative. So it'll be 2 minus x over 2x 2 plus x. This simplifies again to the limit as x goes to 0 of negative x over 2x 2 plus x. Now, this still looks ugly, but it's actually okay. Why is it okay? What was the number that I couldn't use? The number that I plugged in that failed was 0, wasn't it? And check it out. We have found our 0. That's what gave us 0 over 0. And if we divide that, we no longer have to worry about undefined. So I'm going to divide that out. See you later. Rewriting the problem. We have the limit as x approaches 0 of negative 1 over 2 plus x. Okay, so let me reiterate what we did. We first saw the problem and looked ugly, and we cried. We still plugged in the 0. When I plugged in the 0, we realized it was indeterminate because it was 0 divided by 0. We said, okay, since this is a fraction problem, I hate fractions. So I'm going to multiply by the common denominator to get rid of each of these fractions. I took the 2 plus x and I took the 2 so that when I multiply them out, all the fractions go away. Once we're here, we simplify the problem and we realize that the 0 over 0 is actually revealed. We divide those out, we simplify the problem, and our last step here is to now we can plug in that limit, and the limit is 0 equals to the limit as x approaches 0 of negative 1 over 2 plus 0. We're left with negative 1 over 4. Man, that 1 over 4 is a popular answer. Okay, so we're going to jump on one of our trig identities. So this is our sine identity, sine x over x identity. Okay, now if you ever see sine x and x on the bottom, excuse me, we know we have a problem. And this identity here is going to be this. The limit as x approaches 0 of sine x over x is going to be, by definition for us, 1. There is a way for us to prove this, but right now I'm going to say this out. This is, just believe it. Just believe it. Now, sine x doesn't divide by x, okay? And if you went ahead and graphed it, and I would show this right now, but we're running out of time, the graph would look like this. Where this is 1. So looking at the graph here, what does the y value look like it should be as x approaches 0? As x approaches 0 from both sides, the y value looks like it should be 1. Okay, it looks like it should be 1. But can I really divide by 0? No, so the value doesn't exist there. So there's going to be a hole there, but it still looks like it should be 1. So this is our basis for a lot of our limits when it comes to sine x, or even other ones that we're going to derive from this. So let's go ahead and come up with an example. What if I write the limit of x approaches 0 of sine x over 3x? So one of the things about limits is that if we have a constant, we can rewrite it as limit as x approaches 0 with a 1/3 in the front now. See, isn't 3 just multiplying the denominator? That's the same thing as 1 over 3. So if I move that to the front, don't we know what the answer of sine x over x is? Yeah, we said the limit as x approaches 0 is going to be 1. So if I can somehow rewrite the problem to have sine x over x by itself, that's always going to be 1. Let me rewrite another problem. Limit as x approaches 0 of 2 sine of x over 3x. Okay. 2 and 3 is a constant. That's 2/3. This is 2/3. The limit as x approaches 0 of sine x over x. We know what sine x over x is as x approaches 0. Okay. All right. So I need to hurry up and finish this. Now, what if I mix it up? What if I write sine of 2x over x? Wait. There's a 2x now. Now, by definition, it must be x inside and x outside. Remember, x is a variable and it can shift to be whatever you want. As long as it's the same number. Let's go back up here and I'll write something. If this is 3, this is 3, this rule still works because it's the same value. 3x and 3x, it's the same value. If this was 13 and 13, it still works as long as it's the same value. Now looking down here, I see a 2. What number should be on the outside? It should be a 2, right? This should be a 2. If I want this rule to work, I need a 2. But in math, you can't just write random numbers in. You have to cheat it. So this is what I'm going to do. I'm going to write, please look at what I'm going to do to make this work in my brain. If I want a 2 on bottom, I need to write a 2 on top. And this becomes, rewriting it, I want the limit as x approaches 0 of sine 2x over 2x, right? We want these values to be exactly the same. We want those values to be exactly the same. Now, don't we have an extra floating value now? We have this 2 back here. That 2 goes in the front. Now, going back to our definition, what is this here going to equal to? Back to 1. If I can rewrite this as sine 2x over 2x, sine 5x over 5x, sine whatever you want. The whole idea, it's the limit as, let's say u approaches 0 of sine u over u. Whatever you want to plug in, if you can plug it in, this is going to equal to 1.